Okay.
Hello, good morning. There are two more homeworks due for the course in the last 2 weeks of classes. And one is due on Monday. And the second one, which is the last homework, is optional. But notice the dates, this is due on Friday, not the day of a lecture, and it's midnight. And it is optional. This deadline is not very strict. It's available almost at least 24 hours into the holidays, but officially I cannot make homework due beyond Friday, so that's the official day of the due date. There's a final exam. Number 12, it's Monday. 2:45. This will be about 50 to 60% before midterm 3, and about 40%, 50-50% after. It's also, I should point out that in the final exam, there are 2 questions that I always ask exactly the same topic on the question, except that or I haven't taught you yet this, we will be talking about lenses and mirrors. There will be surely a question on a lens, and there will surely be a question on mirror. If you look into the past papers, you will see that it's the same thing that comes, except I changed the type of mirror, where the object is kept, and so on. But if you understand ray diagram, that's what it is called, you can surely know exactly what's the format of at least 2 questions is going to be. And we have about 8 questions, so 2 questions is a good number. So we so out of this, about 20% you can know what to expect. So if you have questions on that, if I'm not being clear, feel free to ask me again. But I'll elaborate on that as we proceed into the video. I also need to do an evaluation for the course today. It will be done in the last 10 minutes, so I'll finish early. But I need a volunteer who will administer the evaluation, basically distribute these sheets of paper, make sure everything finishes, collect it back, and then you have to give it to the physics office. Physics office is on the 4th floor, right when if you were to enter the auditorium from the back side. So it's about 20 feet or 30 feet into it. So I need a volunteer for that. So if anyone could agree to this.
Okay, Anthony, do it right now.
In the last 10 minutes, let's say I will, I'm sure I'll finish earlier than that. Any other comments or questions you have concerning the post? Okay. We have been talking about electricity and magnetism in the first about 6 weeks or so. We concentrated on electric property of materials, how they act under what is called electric field. If there is an electric field, it exerts a force on on a charge, if you want. And in other words, if there are two charges, one charge creates an electric field, and the electric field exerts a force on a second charge. Same thing works for magnetism. A moving charge creates a magnetic field and it exerts a force on another moving charge. These are described inside a material by two properties. One is epsilon naught, which this is permittivity. Of vacuum. If you have nothing, that's what we mean by vacuum, and there is an electric property to that. If you fill it with a material, for example, plastic or a metal, then it will get upgraded to epsilon. So it is no more, we don't write the subscript 0 there underneath, and that's called the electric property of a material. Mu naught similarly is called permeability of vacuum. And if you have a material instead of a vacuum, it is called mu. So this is the electric property, that's the magnetic property. And we have noticed that remarkably, it was not expected at all, that these two together have speed of light in it, and it seems to suggest that light as we see, the speed of light in vacuum, is which was always considered an entirely different concept, entirely different phenomena, is actually nothing but electric and magnetic effects playing together. So that is our understanding, and now we want to switch from electricity and magnetism and do what is called optics. In fact, we will do ray optics. I'll describe what ray means there. Optics is the field where we talk about light, how light interacts with materials, and we will notice that since light itself is electric and magnetic field, anytime you see the charge or a metal, it behaves according to what we know electric and magnetic field does. So that's going to be our idea. Remember that an electromagnetic wave is, so this is a direction of propagation. Direction of propagation of the wave. If you think of an ocean wave, even though the oscillations of the water particles is happening in the vertical direction, in the direction of gravity, the wave actually is propagating horizontally, perpendicular to that. Similarly, the electric and magnetic field are oscillating perpendicular to the direction of propagation. That's your electric field. So that's electric field. And one and magnetic field is perpendicular. So that's your magnetic. And electric and magnetic field are really coupled with each other. How are they sustaining each other when there are no charges around? There is a change in the electric field, start from 0, goes to maximum
then it comes down to a negative of the maximum. This change in electric field creates a magnetic field. And the change in the magnetic field in turn creates the electric field. And this interchange between them sustains them. You don't need a charge at all, and electric and magnetic field can stay just on its own. Change in electric field creates magnetic field, change in magnetic field creates electric field. So that's it. That's a mode that takes a light on its own, and that's what we understand by light. Like when we see light around us, the brightness that we see around us, it is propagating, it is existing all over space. It is not localized like we have an electron or a proton, which we always understand as occupying a fixed amount of space. This is like an ocean wave. It starts from somewhere negative infinity and goes all the way to positive infinity, and it's not that it is surviving only to here, it's that everywhere. It's filling the whole of space. And that's our understanding of light. But we want to describe this as not as a wave, but what approximation can we treat a wave as simply a direction. So that is a direction of propagation, and we do not want to have too many details about what is the wavelength of the amplitude of that. What circumstances can we ignore that? And that's going to be this is the wavelength, remember, this is the wavelength of light. If the wavelength of light is lambda is very much large, so this means much larger than, make it 100 times. So that's if you want to be in 1% accuracy, that's significantly larger than the irregularities that you see at interfaces, or let's say particles. When light is going through the room, it is actually encountering a lot of atoms in the atmosphere. If the size of those atoms are smaller than the wavelength of this oscillation that we have here, then we can approximate this to be just a straight line. So we want to say is much larger than d, where d is irregularities. In medium or the interface. Medium is sufficient, but here we will be talking about what happens when it comes and hits the surface. For example, how does light behave when you see a mirror, right? Or in fact, what is the mirror in itself? That's what we want to talk about. So we will be more interested in the interface. So if the mirror is not smooth enough, how does light behave? So these are small irregularities on the surface of the mirror, if you want. If that is true, and lambda will be our visible light, so lambda or visible light, By visible light, I mean what is visible to us. Our eyes are usually sensitive to somewhere between 400 to 700 nanometers. Visible light. For visible light, lambda is approximately 400 to 700 nanometers. That's the type of a bacteria. So that's the simple way of saying it. And that's why we use light to see bacteria. We cannot see virus very easily because they are too highly because light is not sufficient, or visible light cannot be used to see bacteria. For that, you need other smaller wavelengths of it. So since we will be using, or we will be working mostly with visible light in the next 2 weeks, we want to have surfaces that are smoother than 400 to 700 nanometers. That means a surface that is much more smoother than a bacteria, type of a bacteria. That could be any irregularities of that scale. So that has to be very smooth, and we will talk about how we can generate that. It will be relatively easy. In that scenario, what happens? So that's ray optics stuff. In that scenario, this oscillation that we have You don't have to talk about that, we just say it's a straight line. So that's a ray, so we forget the whole wave, we do not talk about the wave at all, instead, we have just a ray. This is a ray of light. It doesn't mean that light is concentrated along this line, it just means that the wave is moving in that direction. Imagine an ocean wave moving in the X direction, that means that this is the line of propagation, and that's all we need to know about that ray for our purposes. We do not need to know how high the amplitude is, so how high the amplitude is, how much energy is concentrated in it. We are not interested in that. We are only interested in that direction of propagation. And we will see that when the irregularities are really small, we can do a lot of properties of what will happen to this light after it reaches an interface. For example, when you're standing in front of the mirror, you look like yourself, but sometimes you would see that if the mirror was slightly curved, then you look different. Sometimes you're smaller, sometimes you're taller, and it can be weird shapes. And what decides those shapes? That's what we will be interested in. And as far as mathematical background is needed, what is needed here is the geometry of a straight line and the geometry of a circle. That's all we will need in this next few weeks. How does straight lines interact with the geometry of a circle? That's all that we'll be using. So there will be a lot of geometry at this point, but the property of a straight line is what will come into picture. So that's the ray of light we will have. Now, how does our let's begin by saying, how does this ray of light interact with a mirror? So first of all, I need to define what is a mirror. So what is a mirror, by the way? How would you build a mirror? Maybe surface. Any surface off? Reflecting surface, that's a terminology. Is glass important in the mirror? Maybe I can make it more precise my question. How important is the glass in the mirror? Sorry? I cannot hear you guys. Like, you guys let's louder.
Like a gray surface with a glass pan plane in front of it.
Yeah, what is that behind the glass?
Gray surface.
Great surface. Is that what it is?
A gray painted surface.
Painted surface. Yeah, what is that painted surface? Yeah. So the point is that it's not the glass that is important at all. Right behind the glass, you will see that there is as Benjamin pointed out, that there is a painted surface. That's actually a metal. In the olden days, it was metal that was used for mirrors. So any polished metal, remember, we're talking about electric and magnetic field. They interact with charged particles, and metals have charged particles. So we need charges inside a metal. That's what is more important. So behind the mirror, it is a metallic surface that has been coated. Earlier, they polished a mirror or polished a metal to construct a mirror, which was very expensive. But then they realized you need only the surface of the mirror. So just spray the metal on a glass. So glass is just a substrate that serves the function of the metal or metallic surface is put on the glass. That's all that it does. So it is the metallic surface. So any metallic surface is what a mirror is. So what is the mirror? It is a metal, a metallic surface. But you need to have this feature that the irregularities on that metallic surface has to be small compared to the wavelength. With D very much small compared to the wavelength. So whenever we say it is a mirror, we have to talk about which light are we going to use. If you are using an X-ray, then this irregularities have to be really tiny, it has to be of atomic scale. If you're using January, then it has to be of a proton scale, very hard, almost impossible to do that. But as far as you're using a wave, the irregularities have to be much smaller than that lambda, and that's a mirror in principle, and a metallic mirror if you're using electromagnetic wave, because that's what interacts with that. So for our purposes, a mirror, so how we will represent a mirror is, so that is this represents the glass sheet that we look into it, but at the back side of the mirror, there is a coating, that's a metallic coating, and this will be represented as that metallic coating. So this is the front side. That's the front side of the mirror, and that's the back side. So metal is on this, so you color it so that it is actually opaque on that. And is that clear? So this is basically a metal, and for our purposes, I've chosen a flat sheet, but it can be curved of any geometry in principle. Then we want to know so now we have light and we have mirror. Now we want to talk about how does the light interact with the mirror, and we also want to talk about how does light look to us. That means our eyes come into picture, and we want to talk about how does an eye interpret the light that is coming into our that is entering our eyes. So before I talk about light interacting with the mirror, so let me talk about eyes. So how our eye interprets a very simplistic picture. We won't go into the details of how our eye functions. That's not my goal. A very simple idea of this ray. How is it interpreted by us? So let's begin by the term object. So this is a technical term. So in optics, we will deal with an object that will be a source of light. So this is a source of light. So, but that's not sufficient. We need to talk in terms of this rays. In what sense is it a source of light? Start a point in space. If there are these rays of light coming out of this point, that means it's an object. So there is light rays coming out, then this is an object. So that's an object. But example is electric bulb, a light bulb. Typically, it is not oriented on one side, it is actually going in all directions. But you can have oriented sources of light also. So for our purposes, whenever there are rays of light converging to a point, that means probably there is an object in there. We will pick only two of them, and that is sufficient. So that if there are two rays of light coming out of an object, that's good enough. I need to specify what this point is, and I only need two rays of light. So ray 1 and ray 2. That's ray 1, ray 2, any two rays. Out of many of these rays, I pick two rays of light. Wherever they meet, that's going to be my object. So that's a source of light. So now I have a source of electromagnetic waves, which has been approximated into a ray, into a straight line. That's all. Next, we want to talk about an image. Right? So now an image Now, for an image, our eye comes into picture. So this is our eye. So that's our eye. How do we interpret and what we see? There are rays of light that is entering our eyes. Let's imagine two such rays. But there are lots of rays that is entering our eyes, but usually they form a cone, and our brain is smart enough to realize that whenever light is coming in a cone, our eye interprets only these two. There is sensation of only these 2 points. It doesn't really know that light is coming from here. That is an interpretation of our brain. It projects it backward. It is smart enough to draw a straight line and realize that there is an intersection of these 2 lines. So this point here, which need not really be an object, light could be coming from here. Notice the difference between this. This is the source. Light is going in all directions. Instead, there are 2 rays of light that come and intersect and cross each other. At this point, there need not be an object. Even without an object, there are 2 rays that can cross, 2 waves can cross each other, and this will be interpreted as an image. That means to say that whenever light is not originating from that point, but nevertheless we interpret that as a point of origin, then that will be an image. There is a better version of this. So for that purpose, let's bring in our mirror. Right? We always see an object inside the mirror. Does an object exist? Like I see myself in the mirror in the morning. Do I exist there? Do a parallel me exist there? That's an perception made by my eye. So that's what we mean by an image. And how do we see that? So let's look at the mirror more closely. So that's your mirror. So this is a flat mirror. A bathroom mirror typically is flat unless it has been curved. Weather conditions have made it curved. So let's say a perfectly flat mirror. So that's a plane. And we have an object now. That's your object. That means it's a source of light. Whenever you have a source of light, draw 2 rays. That's your first ray. And if possible, draw another ray. I'm being judicial here. From experience, I know that I have which rays to pick. That's what we will learn in the next 2 weeks. As to which are the rays you want to pick out of all possible lines that could have emitted from this object. Some of these lines are convenient for geometric purposes. So I picked 2 rays. One is perpendicular to this, and one is making an angle with respect to the surface or the interface. This ray, as we will see in a few minutes, we will define what is the property of reflection. This reflects back. So this is striking and it comes back. So it's bent, hit the surface and came back. That's your ray 1. So this is your object. Goes to the surface, a straight line, it using properties of reflection, which we will define in a few minutes. It comes back and then it keeps going in this direction. That's ray 1. The second ray goes all the way to the surface, and it turns out that it reflects back as if it is a ball is reflecting off the surface, and we will talk about that in a few minutes, and it will be like this. So that's your ray of light. So that's ray 2. That's what is happening to 2 of the rays, and the object is here. So there is an electric bulb here that is sitting there, or it could be you standing here. Light comes and falls on you. Once light falls on you, you act like a act like an object or a source of light because things are reflecting off you. So that's your two rays. But now this is a cone, right? I said whenever there is a cone of light, our eye is smart enough to project it backward. That is how we perceive our world. This is a cone now. So notice that's our eye. That's a magnified version of our eye. That's your eye. And I want to clarify that this is the cone. Two rays of light. That's your two rays of light. Our brain, only thing it knows is whenever light comes in, it projects back. So it will project those two rays backward. It doesn't know that there is no world beyond the mirror, so it projects it backward. And wherever it peaks, that's what we think the object is, which we should call it an image. Because light really cannot go inside the mirror. It is all reflecting off. Light doesn't exist behind this. It is dark out there, but our brain, in a sense, is cheated to realize that there is actually a image there. So that's your image. That's a perception made by our brain. And that's what we would like to know. In the next 2 weeks, we would like to know if mirror was curved. We will restrict ourselves to spherical surfaces, not any surface. In principle, you could consider an ellipsoid, parabolic mirror, all those are possible. But we will say if this was a spherical mirror, where is the image formed? That means to say that if you were standing here, where do you see the image? That's going to be our broad goal. So it requires few definitions. That's your object, image. Notice again, images where light seems to be crossing, but not necessarily that there is an object there. In fact, there could be no object there. Still, our brain thinks that, or our brain interprets there to be an image there. This looks a little bent. This could be a straight line there. And it turns out that if the geometry was correct, if this was 90 degrees, everything worked out fine. This would be exactly the same distance behind the mirror. So next time you look yourself in the mirror, you can ask how far is your mirror behind the mirror. Usually we think it is on the surface of the mirror itself. No, that is a perception we make of the depth inside the mirror too. We can really think of a depth inside the mirror, and that's the perception. And so that's what we want to talk about: objects, images, and we will also have to talk about the properties of this mirror itself, and that will be decided by the curvature of the mirror. I said we will talk about spherical surfaces. We will talk about the radius of the sphere. So that will play an important role. And often when we are talking about glasses of our eye, we talk about the power in the glasses. That's the property that we decide. When we say that we want a glass of particular power, we are deciding how curved is this, how much curved it is. We are not talking about mirrors there it is lenses, but it's the same idea. We talk about the curvature of that surface, and that is decided by the radius of that surface. And half of that radius will be the focal length that we will talk about. So that's going to be the broad ideas. So let me begin by talking why did this ray actually reflect off, and it will be stated as a law here. So let's say this is law of reflection. We have said an electromagnetic wave is electric and magnetic field, and it interacts with metals. A classic example is an antenna, radio antenna, whether it is a receiving antenna or an emitting antenna that does the same job. And then the details of the structure of the antenna is important because the radio wave typically is of the length of centimeters or meters or sometimes even kilometers. So the size of the object is not small compared to the wavelength. So then you have to do a detailed calculation. But in the approximation that the size of the objects is really tiny, you have the luxury of approximating a wave as a straight line, and things get very simple, and we do not have to do those calculations, and instead we just have to say if there is a planar surface, even though I say it is a planar surface, any tiny element of a curved surface is basically a plane. Like our Earth, for our purposes, whenever we do dynamic equations, when I draw a ball, I approximate this to be a flat surface. We pretty much say our Earth is flat in all our calculations. Whenever we say that acceleration due to gravity is 9.8 meters per second squared to 2 significant digits, our Earth is really flat. That's why it is really hard to convince someone that Earth is actually not flat, it is spherical, because you have to do an experiment which is more than 2 significant digits. Very hard. If you want more than 1% accuracy in your experiment, that's really hard, a lot of work. So that's why it is usually harder to convince someone that Earth is actually spherical. So in that sense, we are saying, even though we say it's a flat surface, it is applicable whenever a surface is relatively with that tiny differential element, it is actually flat. And we would like to talk about a ray of light coming in, and how does it go? After it hits after it reaches the interface, how does it interact? And we are restricting our analysis to a surface which is mirror, that means metal. And remember, we are talking about perfect metals. Electric field cannot enter a metal. Electric and magnetic field cannot enter a metal. Electric field is zero inside a metal. So the condition is that it is mirror, right? The tiny surface that is painted behind the glass of a mirror, electric field cannot enter it. So it has to all go back. The serious calculation, if you were really designing an antenna, that requires a laborious calculation. But in this approximation, it's very straightforward, and it is given by a normal line is perpendicular line to the interface. So that's the normal line. This will be called the incident ray. And we want to talk about where does this ray go afterwards. It goes in such a way that angle theta is exactly the same after it reflects. That's angle theta. That's reflected. So law of reflection has 2 points to it. First point is that this is angle, let's say angle of incidence, let's call it, and this is angle of reflection. So theta I is equal to theta R. That means angle of incidence is equal to angle of reflection. It is usually when you're not paying attention, since normal line is an abstract line, the physical feature of this mirror is the flat surface. It is usually more, or it is, if you're not careful, you tend to think that this is the angle of incidence, because that's more physical This is an abstract line, it is not usually given in a problem or when you are analyzing a problem. This is not there to begin with. So often people make a mistake that you say this is the angle of incidence. But that by definition, angle of incidence is with respect to the normal line. It's just a matter of definition. The other angle is 90 minus that angle. And the angle of reflection again is with respect to the normal line. All the angles we will talk about in optics will be with respect to the normal. But notice this is not sufficient. This doesn't clearly state where the ray is going to lead, because when the ray comes here, it is necessary to imagine this to be a plane. There is a whole cone. So you imagine there could be a cone here, and they all have this angle of incidence equal to angle of reflection. So we need to make one more statement. That's incident ray, reflected ray, and normal line or ray, normal line are coplanar. So for example, I could have come here and I could have gone out of the board, maintaining that angle theta equal to theta r. So I want to avoid that. I want to put that restriction in and to say that that's coplanar. So whatever plane it is coming in, that is the same plane it goes. So that's going to be our law of reflection. And if you notice, I have already used that in here. So a simple, this is again a mirror. This is a flat. Light comes here and draw a normal line, and it goes there. But if there is a source of light there, it can also go and hit all the way straight down there. And now the angle of incidence is 0. It's because the normal line is exactly the same. So angle of reflection will also be the same. So that goes this way. But you don't have to pick that. That's a convenient ray to pick, because then I get this nice triangle of that. But typically it is more common to use a small pencil cone, and instead of this ray, you can actually pick 2 rays. Our ray only needs 2 rays. A third ray only helps it to make it more precise. So the second ray could be that, and again do the same angle of reflection. If this angle, so this will be a larger angle, so that means this will be smaller. So relative to this, that will be slightly smaller, and this will actually form a cone. So notice that the cone that is formed, and I can use these two, my eyes can use these two to interpret where the object is. Any two straight lines, when projected backward, wherever it meets, that's where we think our work is. That's your image again. That's your image. Notice that precision plays a very important role. Even with a bit of experience that I have, notice that is, I'm pretty much making it intersect here. Even a small slant can make the results very hard. So I highly recommend that you use a ruler for drawing these images in your homework and in your exam specifically. I said there are 2 problems going to be there, and both the problems require you to draw an image, or sorry, draw a ray diagram. And the precision in those problems plays an important role. So bring a ruler. If you forget to bring a ruler, hold a sheet of paper, and you can make a ruler out of that. Just roll a sheet of paper and make a flat that serves as a ruler. that should be sufficient. If you need, I can provide you with papers. I will not be bringing rulers. So make sure you bring in a ruler for your convenience. So that's an image formed from a flat mirror. But often we might have seen that whenever you go to some of the science centers, there are these corners or small rooms where you see a lot of images of yourself. You enter there and you see 50 of yourself, and sometimes it can be infinite images. You can form one image to form another image. So how do you construct that? So a simple scenario could be well, let's have an example. So we have two mirrors. Which is exactly making 90 degrees. And here. So you could imagine the corner of your bathroom where there are two mirrors, right? So on both sides that come and make a 90 degree, you place two mirrors there. That's your mirror. And let's say you stand in front of this mirror, and let's not stand equidistant. Let's say you're closer to this mirror over the other. So that's you being, let's say that's the eye, right? That's your that's your eye. Let us say, or our object. So let's not say it's an eye. Let's say your thumb. You lift your thumb, and that's the thumb that we are going to follow. So that's your object. And the question we can ask is, there are how many images that are formed using this through mirror? So we have to use the same idea, follow two rays, and then whenever you keep an eye projected backward, how many images can you form? One of the possibilities is that let's look at it this way. So that's your one of the rays, and that would be another ray going here. And whenever it reflects back, that could be an image. So that's your first ray getting reflected. Basically, what I'm doing is that I'm making a normal line, making sure this angle is exactly the same as that angle. Do the same thing for the second ray, and it makes a cone. And if you had an eye, that's my thumb. So I move my head and I try to look for these two rays, or I try to interpret those two rays, and my brain thinks that, oh, that's projected backward here, and there's an image. So that's your object. That's image one. So let's say this is mirror one. So mirror one takes a image one, and let's say this is mirror two. And the same thing I can do on here. So that's my one of the rays, and very close to that from another ray. A cone of light, but my head is down here, so I need to reflect this back. Again, use the fact that angle of incidence has to be equal to angle of reflection. So that's the reflected ray, and here reflected ray. So again, there is a cone form. Now you move your head, notice your eyes are here, that's your thumb. You move your head here and there, and this time, if you were to look in this direction, you see another of your thumb, so that will be somewhere here. So that's image two. Okay. Those two images are obvious, two mirrors, there will be two images formed, but there is also a possibility that light comes and reflects here. On the first mirror, gets reflected, that's your a normal line that gets reflected here. And now it again gets reflected off the second mirror. Again, you draw a normal line, and that's your rate. And again, make a cone. If I have to project it backward, I need a cone. So I take another ray of light. Oh, sorry, I couldn't be beginning here. My bad. I start from here. At the cone, it becomes bigger and even bigger. And if I were to project these two lines backward, it turns out that actually as of image 2, which was a reflection of mirror 2, is again reflected by mirror 1. So that will be somewhere here. If I were to do this precisely, this will meet in here. So that's just image 3. Notice that this has been reflected twice, and due to that reason, every time there is a reflection, ideally speaking, all the light should get reflected, but practically speaking, a little bit of light is lost. It is only about 2% or so. Normal mirrors, most of the light is reflected back, but 2% or so is absorbed, and so it is faded a little. So this one, if you were to see it very carefully, this image will be slightly less in intensity because it lost some of the light. But then you would say that, oh, that's okay, but what about image 3 getting reflected now again with one of those two mirrors? And if you notice, because of the symmetry, because this is 90 degrees, these images, again, image 3, now image 2 got reflected in image 3. Image 3, if it were to get reflected off 2, it will form image 1. So they start duplicating themselves. In that sense, they should be brighter. And these will all be slightly more brighter. But if you add that series of 1 plus 1 by 2 plus 1 by 4 plus 1 by 8, so there are multiple images formed there. You don't realize it, but the intensity is not that significant. For example, if you were to add 1 plus 1 by 2, that is then 50% of the light. It is doubling by 50. It is not usually that, it is only a tiny bit. But if you were to add all this up, it's not that it becomes infinity. Even though there are infinite images formed, it doesn't necessarily mean that it will be infinitely intensive. If you add all these numbers, how much is this equal to? Anyone? 1 plus 1 by 2 plus 1 by 4 and so on. But it's turns out to be 2, right? It's not significantly large or small, it's just a factor of 2. In this case, it's actually 1 plus about 1 by 16 or so. It is only about 1 point something. So it is slightly more intense, the image that you see with a single mirror versus if you had 2 mirrors, it would be slightly better image if you superimpose perfectly correctly. It's only about 10% or probably even less. But there is a bigger challenge that we have to superimpose exactly. And most of the time that is not really easy because even a very tiny small angular error in here will start making this slightly fuzzy. So these images will not be perfect, instead it will get fuzzy. So that's how you would analyze a ray diagram for mirrors. These are all flat mirrors. But now we want to talk about spherical mirrors. We want to do similar analysis for spherical mirrors, and we will restrict ourselves to just single reflection. You already see that if there are multiple reflections, it very quickly gets more complicated. We can, using the ideas that we will develop here, it can be done for multiple mirrors. You can have 10 mirrors, or you can have a series of mirrors. That's how devices are made, or instruments are made. Telescope, microscope, they all have mirrors or lenses, typically more than one. Here we will analyze one, so the basic principles are being learned, but you compound them just exactly like a series resistor once you know how one resistor behaves, you can use the same tricks to build complicated circuits. Similarly, we will work with a single spherical mirror. There will be two types of them, but you can easily compound them and make instruments like microscope and telescopes. But we won't deal too much with that. We'll restrict ourselves to simple analysis. Okay. I said the surface of the mirror could be of any shape. Imagine parabolically shaped mirror, ellipsoidal shaped mirrors, but they are all more sophisticated. You need more sophisticated geometry. The easiest geometry we know is that of a sphere or a circle, and that's why we restrict our analysis to circle. Of it, then it is basically circular geometry that we will have. So we'll talk about two mirrors. One will be concave mirrors. So how do you distinguish a concave mirror? So first of all, we need a direction of light. So this will be called oh, that's great, but yeah, the direction of light. Optical. Okay, I forget, doesn't matter. Light goes in that direction, probably will come to my head. Because I need it because whenever we keep a mirror, if I keep a mirror in this direction versus if the light was coming in this direction, then it doesn't work. So in that sense. Yeah, let's call it direction of propagation. In optics, that is a specific word for that. Okay. So yeah, let's say it is direction of propagation. Concave mirror will be a mirror kept this way. So this is a basically a sphere, but it is part of a spherical surface. It is not necessarily a full sphere. Actually, we do in Chicago. There is this nicely, very artistically shaped metal basically, where you can see almost the whole city reflection in there. So that's pretty much a complicated shaped mirror. But we are saying it is a sphere. That means it has a radius r. That's the center. This is the center of this mirror surface, that we call center of curvature. This will be called the radius of curvature, or will be the radius of curvature. And it will turn out that R over 2 will be playing a more important role, and we will call that F, the focal length. Or you can say focal point or focal length. Focal point, let's say this one. For now, let's say this is the point. Let's F. So where is my concave mirror? That's this. So it's a part of a sphere. It is not really an arc. It is a surface, a tiny opening of the surface. And in our approximation, we will have to say that it is a tiny, very tiny surface. If you want to make it bigger, we will be very soon using small angle approximation, and it won't perfectly work. All the equations that we do, they will be too simplistic. They work only in the small region. It is exactly like saying that our acceleration due to gravity 9.8 works only in a small region of Earth, right? If you go very high, for example, if you go 100 kilometers on the International Space Station, it is not 9.8 meters per second square anymore. But if you go 1 kilometer to 2 kilometers, you're pretty good with saying it is 9.8. Same thing in here, as far as your reflections are happening around this region, and a small region, then your equations will be perfect. So again, there's a concave mirror is in the if you have a direction of propagation and the reflecting surface is such that the cave, right, concave, the light is entering the cave. In that case, it's a concave mirror. There is a radius associated with the sphere, and half of that radius between the center of the lens, or center of the mirror, and the center of curvature, that will be your focal point. And the importance of the focal point we will talk about later. Let's concave mirror. Before I talk more details about concave mirror, let me define the other mirror we will have, and that is convex mirror. Again, that's your direction of propagation, which I'm missing the word for. Well, which I'm missing the word for, but now I could have kept the surface on the, I could have painted the inside of the surface, and the outside of the sphere is what is reflecting, and in that case, I will have this to be the surface, right? So this is the inside of the cave part of the surface is painted or coated with metal, so it is reflecting on the outside. Here, the cave part of the surface is reflecting, so it is a concave mirror. Convex is the outer part of the surface is reflected. Where is your radius of curvature? So take the surface again. That's your complete sphere. That's your center. See, that's the center of curvature. Half of that from the center to the from the center of the mirror to the center of the curvature, half of that is the focal length. So notice the significant difference that focal length is on the front of the mirror. By front, now what do I mean by front? Light is going in that direction, that's the direction of propagation. And wherever it is reflecting, it is going to go back, right? Light clearly will not enter there, because from this point on, it cannot enter it there. So that's your front side of the mirror. And the focal length is on the front side of the mirror for concave, and it is at the back side of the mirror for a convex lens. So we need to have a sign convention now. So the sign convention is going to be, again, I keep calling it. This is going to be the direction of propagation. That is a mirror kept somewhere here. It is going to be a spherical mirror. I did not specify whether it is a convex or a concave mirror. So that's your mirror at this point. I haven't set it. So this is concave or convex, or for that matter, flat. What's the radius of curvature of a flat mirror? It is infinity. So like if you were to have a flat surface, it's actually, you can imagine it to be a part of a very huge sphere. In that sense, the radius of curvature of a flat mirror is infinity. So it also belongs
to the category of spherical mirrors. So we have concave mirrors, convex mirrors, and somewhere in between is a flat mirror. So I think either one of them, and now I need a sign convention, and the sign convention will be on this side. So this will be positive. That is, light is going in towards my right, so that's direction of propagation. And the focal length will be measured positive in the front of the mirror. So this will be called the front side of the mirror, back side of the mirror, and this side is negative. The positive focal length is what is called a concave mirror. Remember, focal length is half of the radius of curvature. If the radius of the mirror, radius center of curvature is on the front side of the mirror, then you say it's a concave mirror, and this is a convex mirror. We will be talking about objects and object distance. Object distance will be the distance between the object and the mirror. So we will say this is object distance. So the mirror with the distance the object is usually say the point object and mirror. That's the object distance, or very simplistically, object distance. In short, it's just object distance. Again, we will measure that to be positive in the front side of the mirror, and this will be negative on the back side of the mirror. You would say, how can you ever have an object on the back side of the mirror? That's not trivial, but nevertheless, it is possible. How can you have a mirror on the back side? Whenever you have a compound system, you can use first mirror to have a mirror object that will be, in practically speaking, on the back side of the second mirror. So it is possible, and that will be called a virtual object. And the usual configuration where the object is on the front side of the mirror, like when you're standing in front of the bathroom mirror, that's called a real object. As I said before, we will not be talking about compound configurations just for simplicity. So we will not have the opportunity to discuss virtual objects too much, but they can exist. Finally, that is the image that is formed. So this is the eye distance between the image. Oh, yeah, I forgot about that. I'll stop here and I'll come back. Sorry about that. Yeah, I said it. Yeah, we have to do evaluations. Thank you, Anthony, for volunteering for this. And thank you. We'll continue on